I got to be up here. Let's go over what was on this test, right? So what's on this test? We've got section 8.3. We've got section 9.1, 9.3, and 9.4. Now, when we covered section 8.3, we also really looked a little bit at 8.4. I don't know if you realize that. But I didn't name the notes that way. I just named it 8.3. So I didn't go back and change it. But we did do a little bit of 8.4. And that was when we looked at, remember a rod that has several forces acting on it when it was in a state of equilibrium and it didn't rotate? That's really what 8.4 was about. 8.3 was just the regular law of torque. Okay? So we've got torque, obviously, as our first thing. 9.1 was Newton's law of gravity. 9.3 was circular motion. And 9.4 was Kepler's laws. We called it planets and their orbits, but those are really the main four things. Torque, Newton's law of gravity, circular motion, and Kepler's three laws. Where was there a lot of math? First three, right? A lot of math here, math here, math here. So I guarantee you could expect mathematically on the test, these can be your math questions right here. One torque, one gravity, one circular motion. Now, the Kepler stuff, we had a little bit of math involved, but it was really simple math. It was proving that tau squared over r, or t squared over r cubed is the same for all planets. So we took the period squared over the average distance and cubed it, and it became a constant. There really wasn't a lot of math involved at all. This was really where the math is going to come from. How about torque? What was torque? What was torque? Formula, definition, example. Give me something about torque. Go ahead. What you got? FR cos theta. Good. FR, RF, whichever. I've always learned an RF. FR cos theta, RF cos theta. R stands for what? This is the key in this chapter. You know what R stands for, right?
The distance between the two centers.
For gravity, it does. Remember, this is what I'm saying. For gravity, you're right. We're on torque right now. What's R for torque?
The radial difference between the center and then the application of force.
Yeah, where it's rotating and where the force is applied. Remember, so with torque, we are looking at an example like this, where an object is rotating about this point, and a force is applied here, and a force is applied here. Remember, R is the distance from where the force is applied to where it's rotating. That would be R1 right there, okay? And the other one on this side would be R2. So R, what did we call it? What was the name for R? What's the word for it that we used?
Lever arm.
The lever arm. Make sense of that real quick. Think about the sensibility of the word lever. What does a lever allow you to do? When have you used a lever before? Have you ever used a lever before? Give me an example.
Is it just when you're trying to get something on so you roll probably use it to
Yeah, that's exactly right. If you want to lift something, get something onto something that's rolling, onto something that's moving. If you've ever got a flat tire and you put the jack under your car, there used to be levers on there. Now it's actually a rotating mechanism that creates a mechanical advantage. It used to be a lever, you can sit there and do it. What else?
Is it RF sine?
RF sine theta, thank you, because it was FD cos theta for work. That's funny, I'm reading a book, and in the book right now they're talking about the way somebody says something impacts whether you believe them or not. And Jake, you said that with such confidence with the cosine that I was like, yeah, cosine theta, but it's definitely sine theta. Cosine was for work, FD cosine theta, torque RF sine theta. Thank you. Thank you for correcting. Please guys, if you see the mistake, I'm correct. She's definitely right, sine theta. So in this book I'm reading, it's like the idea that when somebody says something with such confidence that they seem right, you actually have a tendency to believe them more than you would. Like if I said to you guys something crazy about physics, you probably believe me, right? Because I'm a physics teacher, because of the knowledge that one has, but also the way they deliver it. So I right away I heard coach the way Jake said it. I was like, yeah, that's right, coach. So R is the lever arm, and think about the word lever. When you want to get leverage means you're able to lift or propel or push or move something using leverage. So the lever arm, the further is, the more leverage you get. The more leverage you get. And that's like a crowbar. If you've ever used a crowbar before, a crowbar, you could pry a door open, you could pry a window open because you get a lot of leverage because the crowbar is long. It has a lot of length to it. It has a long R value. F stands for obviously what? F? Force applied. And again, theta is the angle between the force applied and the lever arm. So in this case, this would be theta right here. The angle between the force applied and the lever arm itself. That would be theta. George?
Most of the time, R is given, right?
Most of the time, everything's given except for one thing, and you have to figure out. So I don't want to tell you one thing and it's different on the test. Anything can be not given, but for the most part, if you're looking for things in rotation equilibrium, you're probably going to be asked, where should this force be placed, maybe find R, so that it's not rotating? Or maybe I give you all the dimensions and ask, is it rotating as a result of these two torques? Okay? Or maybe you're trying to find the force needed to cause it not to rotate, or the force needed to rotate. So you can look for anything. I can't really say that it's R is always given there. We have to talk about directionals now. We also talked about directionals. So if I were only looking, so take a look at where I'm pointing to. If I were only cared about this point or this force right here, which way would this thing rotate? If this were the only force acting on it, which way would it rotate for only this force? Yeah, because watch, right? I push down, it's going to go like that. Literally. Remember how to do this? What did I show you in case you forget? Take your pen, hold it where the pivot point is, and literally push down. With that force, push down, and you'll see it rotates counterclockwise. So as a result, let's call that F1. Or no, let's call that, we'll call that F2, because I called this R1 earlier. So as a result, torque 2 goes counterclockwise. Torque 2 goes counterclockwise. How about F1? If I only apply F1, which is over here, it rotates, everybody can obviously see, clockwise. And it rotates clockwise. So clockwise we consider it to be negative torque, and counterclockwise we consider it to be positive torque. That was our assumption of directions. Okay? Just like up is positive and down is negative, that's an assumption that we're making. Why do we do that? We do that so we have some sort of system in place that's consistent amongst all science. We don't want to make up positive or up negative and down positive in one class and then different in another or different in a different topic. So traditionally you accept these values of positive as negatives. So if I were to look at the sum of the torques acting, if I were looking at the sum of the torques acting on this, what we'll see here is that one of them produces positive and one of them produces negative torque. So when we sum them together, we can simply apply that sign. That's all we have to do. Think about the signs themselves. So if I want to think about the sum of the torques, and we say, you know what? We're not sure if this object is rotating. Let's figure out if it is or not. If it's not rotating, what will these numbers add up to? If it's not going to rotate, everybody? 0. I see all your hands shoot up. Good. When it doesn't rotate, they got to add up to 0. But my question to you is this now. Will it rotate? So you actually don't set it equal to 0. You just plug in F and R and all the values and see what you get as an answer. If the answer you get turned out to be positive, it rotates counterclockwise. If the answer you get is negative, it rotates clockwise. So to do that, let's go ahead and apply numbers and values here. In the case where the roller coaster is at the bottom, we've got gravity pulling down and the normal force pushing up. So normal force is acting toward the center. This is at the bottom now, right down here. Gravity is pulling away from the center. And that again would equal mvt squared over r. So depending upon the scenario that you have, we can see here that the formula itself changes. If a force pushes to the center, call it positive. If a force acts away from the center, call it negative. Okay, depends on what's providing that force. What provides the force of gravity? What provides the centripetal force? That gives it away with planets. It's the force of gravity. What provides the centripetal force with, what do we do other examples? An airplane? When it was going through like a little barrel roll or another loop, what was it for an airplane? Anybody remember what they were called? Yeah, air resistance, we called it lift and drag. We use those terms. So what I want you to understand here really is that something provides the centripetal force, whether it's gravity, tension, normal force, lift, drag, the electrostatic force for protons and electrons. Depending upon what the scenario is, it's provided differently.
How many math questions from circular motion is there have?
I mean, you can expect at least one from torque, at least one from circular motion, at least one from Newton's law of gravity. At least one from each, okay? If I give you two from one, maybe I'll have you choose one or something like that. But you can expect at least one of each. Those are the first three topics, really, that we went into. Now, I want you also to recognize that in the lab yesterday that you guys worked on, what did you notice was happening? You were spinning it faster. Take a look at this. This is really important that you come up with this. And because you're not turning it until tomorrow, I can't really go over it with you until I actually see your lab. So I'm going to go over it now. You're spinning this object faster and faster, right? But what was it counteracting? It was counteracting the weight that was hanging. That's what this really is, the hanging weight. The hanging weight provided tension. The tension came from the hanging weight. So this is really tension, but it really came from the hanging weight. Did the hanging weight change ever? The hanging weight, did it ever change? I should see no from everybody. It was the same 50 grams, right, the whole time? So when you spun it faster, what happened to the radius? What did you notice? You spun it faster. What happened to the radius of the rope? It got longer and longer. It increased. Why? Because look, if I increase this and increase this, that's the only way I can keep this constant. Again, the hanging weight provided the force that was pulling down. But I was spinning it faster. So for this to be the same, which it was, it didn't change. If this goes up, this has to go up. Why didn't this change? What was this the mass of? The mass of the rubber stopper. That was not changing. So when you spun it faster, it created a larger radius. Because if these both go up, they didn't go up at the same rate because one is squared and one's not. But if they both go up, that's what can keep the tension or the weight from being the same. So that's why that happened yesterday. Keep that in mind. That helps you with the lab, but it's also going to help you answer questions on your test. Okay, it doesn't have to be the exact lab approach, but I want you to see that if the centripetal force isn't changing and you get faster, you got to be going around a bigger radius. Okay? Now, fun fact, little life lesson for you. How many of you driver's license? Only one? Or permit? Either one. How many of you have driven? All right. So if you've driven before, legally or illegally, because now I just saw hands go up that don't have the permit. Kind of like entrapment there, I guess, right? If you've driven before, or if you've ever driven a car, even when you're in a car, when you go around a turn, what you'll notice is if you take the turn really sharp, you feel a lot of centripetal force on your body. You'll feel your body slam into the door. If your dad or mom has ever been on a road trip and you're in the back seat and they turn sharply, you'll feel your body slide into the door. And you hit the door, right? Well, what's happening is this. They're using a very small turning radius. So they're decreasing R. And what happens to this as a result then? It gets bigger because these are, how are they related, Jake? Indirectly. If you lower the turning radius, you get a really big force felt on your body. So when you're turning your car, if you don't want it to lose friction and slide out, whenever you're going around a turn on like I-95 or highway, you should never move your lanes in. Think about it for a second. Okay? I'll draw a diagram for you so you can see this. You're going around a turn on I-95, and there's a lane here and a lane here. There are 3 lanes. The dashed lines are the 2 outer lanes, and the solid line is the inner lane. If you're going around this turn, and your car is right here, and you suddenly try to move your car into the inner lane, you put your blinker on, right? Your blinker is flashing over and over. You move to the inner lane. What are you doing? You're decreasing your radius. Here's your center. There's the radius. Now you're going to a smaller radius. So you're decreasing the R value and therefore increasing the centripetal or the force that's felt. If that force exceeds friction, what's going to happen to your car? It's going to slip out. You're going to lose traction. So a fun fact here is when you're going around a turn, you should only ever move out lanes, not in. That's why in NASCAR, you see them move in because they want to gain the inner lane. But they have to do it at perfect times. Because if they don't do it right, what happens to those cars? They lose traction, the cars can spin out. You know what I'm saying? Does that make sense? Okay, so when you're going around a turn, you're driving your car later in life, move out lanes, don't move in lanes. To this day, I still hold true whenever I'm driving that. I literally think about it all the time. And if you're a driver, you will feel it. If you try to move in lanes, you're not only going to feel the car, but you're going to feel your body feel more force naturally because you're lowering that radius and increasing the amount of centripetal force felt by your body. You're increasing the G-forces. Okay, I talked about G-forces. G-forces are just things like when you're under an experiment and you're at NASA, if you're going at twice, if you feel twice gravity, you're at 2 Gs. If you feel a force of acceleration of like 30, that's like triple gravity, right? Gravity is what, 9.81? So if you feel 30 meters per second squared of acceleration, you're at 3 Gs. And then eventually the body starts to not be able to withstand a certain amount of G forces. Okay, it's not a new force, it's just a multiple of 9.81. If you have double 9.81, you're at 2 Gs. Triple 9.81, you're at 3 Gs. Okay? Because G is Earth's gravity pull, we think of. So that's it for our mathematical components for this test. Kepler's 3 laws. They're the recent thing we've talked about. The first law simply told us that the sun is at a focal point, the other point is empty space, and that planets travel in elliptical orbits. That's all the first law told us. Different planets have different eccentricities. The Earth is pretty much a circle, so for the Earth, take a look at what happens. Here's the sun, here's the other focal point. When the focal points get closer and closer, the shape gets closer and closer to a circle. What happens when the focal points overlap each other? What happens eventually if you get a circle where the star itself and the other focal point are on the same exact location? What shape do you have? Again, ready? Focal points are spread out, you've got an ellipse. As the focal points get closer, you get less and less of an ellipse, more of a circle. Eventually, the focal points are on top of each other. When that happens, what do you have? A perfect circle. When the focal points line up, you only have one center then. A center is really 2 focal points sitting on top of each other. It's kind of weird to think about because you haven't studied ellipses in math yet. You're going to see this in math. If the centers get closer and closer, if the elliptical focal points get closer and closer and they then overlap, you get one center. When you have one center, you have what's called a locus of points, which is a circle. A locus of points equidistant from the center just simply means that a bunch of points that are the same distance from the center. All right? Second law told us several things. The area swept out by a planet is equal in different time increments. So if it takes 1 month, if it takes 1 month to travel from there to there, this area will be the same as this area if it takes 1 month from here to here. Okay? If it takes 1 month for both of those areas must be equal. So as a result, what can you conclude? What was the one conclusion we came up with from this? It was a big conclusion. Say again? But from that conclusion, I'm saying we came up with one other thing. When does it travel a further distance? In scenario A or scenario B? Not same distance, same area. Area is the same, but distance traveled. Which of these has a further distance?
More distance when you're closer to the sun.
Yeah, take a look physically. Look how far this planet is traveling, right? And then look how far it's traveling. So doesn't it travel further right here? And doesn't it take the same time though? So to travel further in the same time, you must be going faster. So the planet moves faster when it's closer to the sun, which makes sense because gravity is stronger, thus whipping it around quicker. We also talked about seasons. We talked about how in the northern hemisphere, we are in the summer when we're further from the sun. Here's the North Pole, here's the South Pole, there's the prime meridian, I guess, the vertical axis. That's the reason. It's because of the tilt, remember? The South Pole happens to face the sun. The South Pole, the southern hemisphere, faces the sun when it's closer, so they get direct rays. So there's summer here, and there's winter up here. But in this case, now we've got summer when we're further, northern hemisphere, and they've got winter when they're further. It's because of the 23.5-degree tilt. Well,
So does that mean that if you compare our summers to their summers would be warmer than ours?
technically you'd say yes, but what about the Earth that we talked about earlier? The shape is not really an ellipse. It's really pretty much a circle, right? So it's almost insignificant, but you're right. Theirs would have more intensity because it's closer and the rays are more direct, whereas when our rays are direct, it's further. But I'm exaggerating this diagram dramatically, right? So because it's pretty much a circle that the Earth travels in, their summer is not as extreme as it could be had it been more of an ellipse. Good point. Very good conclusion there. Pluto. That's the one that we say is the most. You could actually look up the eccentricity of all the orbits and see. But you don't have to memorize that. I'm not going to ask that kind of a fact. Yeah, that's what we were talking about one class. Who was it? Oh, no. Is Gus in this class or is he in the other section? Okay, yeah. Gus was talking about it being a dwarf planet at one point. Yeah, it is considered a dwarf. But for other reasons, not because it has to do with the moons. Okay? The third and final law had to do with the fact that t squared over r cubed is the same for all planets. So if you want to check to see if something is a planet, you could take the orbital time. This is the time period of orbit. Squared over. This is the average distance from the sun. Cubed. You could check that you get the same value as the Earth or another planet. So if you do this for some given value, you get a number, see if it's the same as the Earth, that would classify it as a planet. That's the third law. We quickly talked about satellites, and we had this formula. You don't have to memorize it, it'll be given, but you need to know how to use it. Okay, this was the last formula we talked about with satellites. That's the only other one I want you to know. Okay? R is the altitude, including the radius of the planet. M is the mass of the central object, and G is G again. Office hours today after school, please come by.